Hello everyone. So in the previous video, we looked into the concept of orbitals as we studied previously about orbits and how orbits is a wrong concept according to Heisenberg's uncertainty principle. That means we need to consider the wave nature of the electrons as well. So we brought in the concept of orbitals, right? So we also were introduced into the Schrodinger wave equation, and I told you the various solutions of it and how they are related to the various orbitals present in an atom. Now, while discussing in the video, I told you that the four quantum numbers that you might have studied in your 11th and 12th are also a direct consequence of the Schrodinger wave equation. Okay, so today in today's video, we will be concentrating on the four quantum numbers and its significance. Okay, so starting with, let us start with the principal quantum number, which is represented by uh, a letter n, a small n. So principal quantum number is a quantum number that was introduced initially by Niels Bohr. Okay, he himself introduced this quantum number, and as we know from the Niels Bohr, this quantum number implies the main energy shell or the level in which the electrons are present. Okay, so indirectly you can tell that they are related to the distance of the electron from the nucleus, and also it also talks about the energy of the electron, because we know that whenever the electron is occupying a particular energy shell or level, it will have an energy which is corresponding to that particular energy level or the shell. Okay, and we know the energy expression from the Bohr, who derived the energy expression, and it was shown in the previous video about the energy expression to be minus 2 pi square me4 divided by 4 pi epsilon naught square n square h square, where this particular term implies the permittivity. Okay, and as you can see here, this energy value is a negative term. Okay, now what are all the values that this principal quantum number can have? They are basically whole numbers like 1, 2, positive whole numbers like 1, 2, 3, and so on. Okay, so this is about the principal quantum number and its significance, that it represents the major stationary states or the energy levels or energy shells around the nucleus. Now, remember one thing, that now onwards we are not going to use the term orbit. We are going to talk in terms of orbitals or energy shell, basically energy shells. When we talk about the principal quantum number, we will be concentrating on the term energy shells or energy levels, because we know that orbit, the concept of orbit is pretty wrong because of the Heisenberg's uncertainty principle. You cannot define a well-defined pathway for a particular motion of the electron. So that is why that particular term we will not be using any further. Okay, we will be just talking about the energy levels or energy shells. Okay, so that is about the principal quantum number. Let us move on to the next quantum number, and that is basically your orbital angular momentum quantum number, or the azimuthal. They are also called as the azimuthal quantum number. It is represented by a letter small l. Please remember these representations, because you should be pretty aware of the quantum number as well as its corresponding representation. Okay, now orbital angular momentum quantum number, as we can understand from the term, it is related to the angular momentum of the electron. So we know that electrons are revolving around the nucleus, so it will always have an angular momentum. So this particular quantum number, that is the orbital angular momentum quantum number, it is coming from the orbital motion of the electron. Now what does it signify? Basically, it signifies the shape of the orbital. Now, I'll be mentioning you the orbitals that each of this azimuthal quantum number represent, but the shape I'll be discussing in the next video. Okay, so this particular quantum number represents the shape of the orbital. Also, since it's associated with orbital angular momentum, some of the energy is associated with the orbital motion of the electron. So the energy that you calculate here using the Bohr expression for energy, part of this energy is coming from the orbital motion of the electron. Okay, so all this is signified is a significance of this particular angular momentum quantum number. Now, what is the values that these can take? Usually, L can have values from 0, 1 to n minus 1. Okay, suppose when I tell n is equal to 1, then the only value that L can have is 0, because n minus 1 in this case is 0. Okay, so when we start numbering from 0, only one value is possible. Okay, now if suppose you have principal quantum number to be 2, then the L values that are possible are basically 2, then 2 minus 1, that is 1. Okay, so next value would be 1. So 0 and 1 would be the one value L values for principal quantum number 2. Similarly, let us do one more. N is equal to 3. So L can have values 0, 1. Now n minus 1 is what? 2. So next value would be 2. Not more than 2 is possible. Okay, so this is how you come to know about the L values corresponding to each of the principal quantum number. Now, an important thing that you here need to understand is the shape. So when you have L value equals to 0, it implies s orbital. Okay, since we know now onwards we will be talking about the orbitals, not the orbits. Okay, so when L value is 0, then that signifies it is a s orbital. Now, what's the shape of these orbitals? I'll be discussing in the next video. So when L value is 1, the orbital that it represents is basically the p orbital. Now, when the L value is 2, it represents the d orbital. When L value is 3, it represents the f orbital. Okay, so these are the orbitals so far we know in our study of atoms. Okay, so we have these values only we will be concentrating on, not the higher terms, because we do not have any atoms corresponding with higher orbitals than this. Okay, so now here I have written down an important point, that it is responsible for the finer lines in the hydrogen spectrum. So when we talked about the drawbacks of the Niels-Bohr's model, we told that one of the drawbacks that the Niels-Bohr model had was that the finer lines, like each of the lines in the hydrogen spectrum, if we visualize them through a more sophisticated instrument, we can see that one single line is made up of many finer lines. Okay, and these finer lines that are coming in the hydrogen spectrum are basically because of the presence of these subshells or suborbitals in the each of this principal quantum number. So Niels Bohr only considered the principal quantum numbers. Now, this concept of orbital motion has brought in that each of these energy shell is associated with multiple orbitals, and that is why you see more finer lines than your single line in a hydrogen spectrum. So finer lines was well explained by the bringing of this particular quantum number, that is orbital angular momentum quantum number. Moving on to the third quantum number that you have to study is the magnetic quantum number, represented by letter M. Okay, and this represents the orientation of the orbitals. Okay, now angular momentum, as we know, they are vector quantities. Okay, so obviously whenever we talk about a vector quantity, it will always have a direction. Okay, so each of the orbital that I just now introduced, that is your s orbital, p orbital, d, and f, they all have a particular different orientations. Okay, and those orientation, like how they are oriented in a three-dimensional space, is given by the magnetic quantum number, which is represented by a letter m. Okay, so for each L value, that is the angular momentum quantum number, how many orientations are possible? You can calculate using this formula, which is 2L plus 1. For example, when we talk about L value 1, which I just now told you that it represents the s orbital. So how many orientations are possible for an s orbital? If you want to calculate, it will be nothing but 2 into what is the value? This is 0. L is equal to 0 means s orbital. So 2 into 0 plus 1. So how many orientations are possible for a s orbital? Only 1, because s is not a directional orbital. It is spherical in shape. So when the orbital is spherical in shape, obviously it won't have any kind of direction. Now, if I suppose talk about L value 1, then it represents my p orbital. Okay, so if I want to calculate how many orientations are possible for a p orbital, it is nothing but 2 into, now L value is 1 plus 1. Okay, so 2 plus 1, it is 3. So there are 3 possible orientations possible for a p orbital. Okay, similarly you can calculate for d and f, which I would like to leave it to you for yourself to find out. Okay, now the values that the m have is given by, like if you have 0, then m will have only one value, that is 0. When L value is nothing but 1, which represents the p orbital, we know there are 3 orientations possible. So what are all the m value that it might have is given by so -1, okay, then 0, then you have the +1. Okay, similarly, when L is equal to 2, which represent the d orbital, okay, m can have values which is nothing but equals to starting from -2, next whole number is -1, then followed by 0, then 1 and 2. So how many orbitals are possible? How many orientations are possible for d orbital? 1, 2, 3, 4, 5. This is another way of finding out how many orbitals are possible for a particular L value. Okay, so for L value 1, we have 3 orbitals possible. For L value 2, that is d orbital, we can have 5 possibilities. Similarly, for f orbitals, we can have 7 orbitals possible. Okay, so each, here I've written, each orientation is degenerate in the absence of magnetic field. So if I talk about p orbital, you have 3 p orbitals possible, which is represented as px and py and pz. Okay, and each of these orbitals is degenerate. That means they are equal in energy. But when you apply the magnetic field, they split into 3 different energy, 3 different orbitals with different energy, and that is why you see a Zeeman effect, that is the influence of the magnetic field on the hydrogen spectrum. That is because these subshells then is moved from their degenerate state to different energies, and that is why you see an effect on the hydrogen spectrum because of Zeeman effect. So that is because the degenerate state of these individual orbitals is affected when you apply a magnetic field. Okay. Then your final quantum number that you have to study is the electron spin quantum number, represented by a letter m with a subscript s. Okay, and this represents the orientation of electron spins, okay, because we know that the electron also can spin, um, uh, uh, spin in its own axis, okay. So the spins that spin orientation that are possible for an electron is given by plus half and a minus half. So if this represent the plus half orientation of the electron, then this would be the minus half orientation of the electron. So only two possible orientations are possible for each of the electron. Okay. So I hope you understood pretty well the four quantum numbers. Please go through this video again. Try to do it yourself. Calculate for each n value, the different possible L values, M values, and then try to understand these quantum numbers pretty much in detail. It's just a revision of whatever you have learned in your 11th and 12th, but still, please brush it up because we'll be discussing more examples in our live session. So I hope you understood this pretty well. So thank you for listening patiently. Have a nice day.